All right, so now we're going through the code for assignment number 4, which is our first time to start using multiple regression using R. So this is a really exciting class because it gets you to use R for the first time to do multiple regression. And that again is the bulk of the course. That's what you really hear. That's the take-home message for this course. It's what you really need to know how to do. So let's go through this. You're using the data set we were using last time with respect to the Carter and Reagan 1980 election. And that's the National Election Studies Panel Study. And let's take a look at what we get when we do the R code. Now, here is the R code. It gets you started, and the rest is up to you. And if any of you know anything about SAS and you want to see the SAS version of this assignment, it's further below. So let's take a look at this. What are we doing here? A lot of it is the same as what we started with. So the first thing we do is that we're reading the table, and we're reading the actual SAS, the data set, which is a data frame in R. And it's called panel80.txt, and I've written it .txt because I keep it as a normal text file. Some instructors like to use other names for it and save it in different formats. Some people like R data as the data set names for it. I like to keep it just as a text file so that you can open it up in any way that you want, and you can understand it to be just a simple text file, just for comprehension purposes. Later on, as you get more proficient in R, you may want to start saving it as an R data file or something else, maybe as a CSV, a comma-separated value file. You're going to choose for yourself. CSV files are probably the best because it's nice to have little commas between all of the data values. And if they have those little commas, you can open those data sets up with Excel and edit them and so on. So I'm not using the attach command, but I'm leaving it there because so many instructors do use the attach command. So just for your own sake of just having it there. And again, the names and the options for scientific notation and not scientific notation. And I'm going to actually show you later on what happens when we suppress scientific notation. So we're going to take this out later on after we get to it. But right now we're going to use the scientific notation. So these two options are actually not necessary. One turns scientific notation off and the other turns it back on. But if I just deleted those two, that would be okay too. The only thing is we wouldn't see the results of playing with the scientific notation. So the only reason for these two lines here is to show you what happens when you use it and when you don't use it. All right, now we're going into the Reagan model. So what we're doing now is we're using a linear model, and that's the LM procedure in R. LM stands for linear model. And of course, the assignment statement here is the less than dash instead of the equal sign. Again, you could use the equal sign, but I strongly recommend you not using it because the convention in R among people who use it is always to assign what's on the left to what's on the right, because sometimes they like to assign what's on the right to the left, or actually onto the left to the right, and then they switch the direction of this like arrow. But in this case, we're going from the right to the left, if I said those directions correctly. And so we're assigning what the model is all on the right to the name that's on the left, okay? And again, if you switch the direction of this arrow, so make it a dash, then followed by a greater than sign, you'll be assigning what's on the left over to the right. But just get used to putting everything that you want on the right and assigning it to the something on the left. Makes things more simple. Now, this is a regression equation, and we're going to actually talk about what this is. However, if you just do a regression equation, it doesn't necessarily mean that you want to see the results. There are times when you just want to do it for the sake of doing it and then use something that's in it somewhere else. You don't always want to see what you're seeing, what you actually have. So for R, it doesn't automatically just show you the results. If you do something in SAS or Stata or SPSF, if you ask for a regression, it assumes that you're going to want to see it, so it shows you the results. With R, it doesn't necessarily show you, so you have to use the summary command. Summary says, tell me what you found. Let me see what you got. All right? So the summary Reagan model, it lets you see everything that's in here. So let's actually talk about this regression statement here, Reagan.model. And I called it Reagan.model not for any particular reason. I used a period just to separate the words Reagan and model. And I just wanted you to know that this is the model where we're going to be looking at Reagan feelings in September during that election in 1980. Feelings for Reagan from the respondents. Okay, so you could have called it Tom, Susie, Joe, but try to use names that you'll remember what it means. If I see Reagan.model, I know exactly what one that is. Okay? Now, what actually is it going to be? It's going to be the LM procedure, which means you're using a linear model. And that's simply the y equals beta naught plus beta 1 times x1 times beta 2 times x2, and so on. That's simply the regression equation that we've been using all along. And there's always a little epsilon at the end of that, and I'll stop writing the little epsilon. That's simply the residual. That's the error for each individual. So in the rest of the course, I won't always write this little Greek letter epsilon or an error or something, but you'll always assume that it's there. So that's our equation, and we have our first variable here, our second here, and our third here in terms of explanatory variables. And here we have the dependent variable on the left inside the parentheses for the LM procedure. So it's LM parentheses and then everything you need, and then N parentheses. So the linear model is going to be inside those parentheses. So your dependent variable is here, and then you have a tilde. I'd like everybody to find the tilde on their keyboard. It is probably in the upper left-hand corner right below the escape key. Tell me if you see it. Let me see nods. Okay, that's a tilde. This tilde is actually the words is modeled as. Okay, so they don't use an equal sign. It means is modeled as. If it was up to me, I probably would have used the equal sign. But they wrote the R program, other people wrote it, and they wanted to have the tilde mean is modeled as. Okay? So what we're having here is Reagan feelings is modeled as, that's what the tilde does, and it's important to note that because you can actually use that tilde for a number of things. There's even a way to create dummy variables using the is modeled as tilde, and I actually show that later on. I don't prefer that method, but it's useful for a variety of things, all of which I normally try to avoid, except in the LM procedure or similar types of procedures. So just remember, is modeled as for that little tilde. And what is it? It's modeled as a function of income, age, and party ID. Notice that you did have to put the actual plus sign. So you're actually putting the plus sign. You're actually writing out the algebra. The only thing you're not putting is the actual parameters. Beta, you're not putting the intercept term in. You're not putting the slope times income, the slope times age, and the slope times party ID. So it's assuming that you're going to want a slope for each one of those. All right? There is a way to avoid that, but it assumes that you want an intercept, so it's putting in an intercept for you without you doing anything about it, and it's assuming that you want the slopes for those variables. Again, there are ways to stop it from doing all that, but in the default mode, which is the normal mode, it does it for you. So you just list the variables, but it does include the plus sign that you have to put in between those things. Some other programs like SAS, it doesn't do that. You just list the variables and it doesn't give you, you don't even have to do the plus sign. But nonetheless, for R, you do put the plus sign. And then you have a comma, and you tell it which data set to use. Now, you could be using a number of data sets, which is why I don't like to use the attach command. But your data is my data, which we got up here. Okay? So that will give you an equation. Ray Feel 3, feelings for Reagan in September, is a function of income, age, and party ID. These are three particularly not very interesting variables. Why did I put them up there? Because I wanted you to find the interesting variables. So I sort of put the sort of stupid variables. This party ID will work fine. Income and age by themselves are sort of, well, you know, it's nothing to write home about. And so we have the summary statement saying, tell me what you found in that thing. Now this layout statement is sort of useless for this particular case. I just wanted to show you that in this beginning stage that R has the ability to plot things in all types of fancy ways. Now we've plotted some things before, but this is a plot where you're actually taking 4 different spots and putting them on a page and putting 4 plots in a row. So we're not going to actually go into this. This is just to show you that you can use a layout statement to arrange the plots, and then you can actually do some fancy things in R. So this is just to say, ooh, ah, but really not. These are actually regression diagnostics, and they're sort of interesting, but not so interesting. So this is the layout that's being used, and then the plot statement goes with this layout statement, and it plots them in a sort of nice row. Again, this is just to show you that R can do a lot of stuff. R can do a tremendous amount of plotting. So I've given you print-ready plots to use already, and those are the ones you really need to know how to do. We did those in earlier assignments. But again, this is just to show you that R can do other types of plotting things. I mean, a zillion other plotting things. So this is just to throw it out there and say, oh wow, it does funky things. So that's what it does. Okay, again, I have to have a Windows command because I'm going to run this in raw R on a PC. For the Mac people, you'd have to delete that, or all of you who are using Rstudio, you delete that Windows command also. Now I have the exact same thing for Carter model. So I just called it Carter model so I'd remember. Now this is the exact same equation as the Reagan model, except that the dependent variable is Carter 3. So I just copied and pasted the Reagan model, summary, layout, plot, these 5 lines. I just copied and pasted them here and just changed the dependent variable to Carfield 3 instead of Rayfield 3 and renamed it Carter model. So it's actually nice to have the same equation for each dependent variable. Rayfield 3, Carfield 3. Some of you may say, well, maybe there's different things driving feelings for Reagan than there are for Carter. So maybe the equation that you have on the right-hand side should be different for Reagan than they should be for Carter. That's a good point. You're probably right. The trouble is, you're my DNA now. So I want to get you used to defending yourself and protecting yourself when you're attacked. And methodologists do that type of thing. So one of the things I want you to know is that when you have 2 equations, 2 models, like of 2 different candidates for the same year, and if the equations are not the same, you have a very great deal of difficulty comparing the 2 equations. You really can't compare the Reagan feelings to the Carter feelings because the equations are the same. And the critics will say your modeling is ad hoc. In methodological circles, the word ad hoc is sort of like throwing a 4-letter word at you, meaning you just sort of thought of something crazy off the whim and did it differently. And they like the idea of it being symmetrical between the 2 models, parallel structures, so that they compare the 2 things. In reality, the stuff that was driving the Reagan election probably was a little different than the stuff that was driving the Carter stuff. So you actually probably could come up with an excuse for doing separate models that look actually different. In which case, from a strategic point of view, when you're presenting your stuff, you're probably better off having 2 parallel models that are exactly the same, and then if you want to change the models so that they're different, have those as well, so that you can always compare 2 identical models with 2 differently structured models, so that the Reagan model is different from the Carter model, because people are always going to, claim that ad hoc claim against you, and you want to be able to show all of that. Many times when you do a presentation of methodological stuff, you want to have done things like 100 different ways and have your PowerPoint presentation that may have 20 slides in it actually have 100 extra slides for different things that you've done, so that, because you don't know what question is going to be asked. So when someone asks a question, you want to be able to say, good question, actually I've already done that, slap up that new PowerPoint slide, number 56 in the list, and say, and the results were no different, you get the same type of results, end of story, go on with your stuff. All right? Because you do have people out there that will attack you for reasons that are just really nuts. And so, the worst kind of thing they'll say is, your modeling is ad hoc. Or I've actually heard situations where people said, well, let's assume you did have results. What would you want to have told us? I mean, I've heard that stuff with my own ears. I mean, insulting to the point of insulting. I mean, it's just, so you have to understand that when you learn statistics, you have to defend yourself. You don't just go in there with a story, one set of tables, one set of results, smile and say, look what I found. You always have to have a reserve of stuff to protect yourself with. You have to be ready for this stuff. So part of that conditioning starts today, starts now, starts when you're taking your first course. Get used to it. It's part of the environment. So the people who will stay quiet are the people who don't know anything about statistics. As soon as the one person, usually a guy, in the back of the room starts getting on your case for whatever reason, the idiots in the room who don't really know anything will start chiming in and seeming like these are people like faculty members at colleges. They try to sound like they're smart. In reality, they're idiots. But they have this one guy sort of charging at you and criticizing you. So they raise their hand and they try to make comments assuming that you're going to be buried. So it's time to pile on, and they think it's safe to pile on. I swear this type of stuff goes on. It's psychology and sort of the masses. And so what you have to do is be ready to fight back. You want to be pleasant. You want to be strong, you want to be assertive, but you have to be ready. Does everybody hear that? You're my DNA now. When you do a methodological presentation, you have to sit down with your advisor beforehand and say, what is every possible criticism that could be made, even if it's stupid, even if it's wild? Give it to me. Make a list and have those extra PowerPoint slides ready to go. Everybody heard that? You could give 20 presentations, but one of them will be, you're going to be dragged out like you're unconscious if you're not ready for it. If you're ready for it, it'll be a peak experience. You'll remember it, okay? You don't want to go through that experience where you're dragged out like you're unconscious. You want to be ready for it. It will happen one day. Just understand, it will happen. So you must get ready for it whenever you do all of your stuff. And that includes footnotes, endnotes, stuff like that when you write your dissertation, when you write your articles, to cover all of these possibilities. People always ask these things. All right. So then, after we do these two models, okay, we go into the standardized variables. Now let's hold off on that. I do it all again to get the standardized regression coefficients. But let's first just get the normal regression coefficients. You always need those first. All right, so actually let's go and copy and paste everything from the very first line down to the last plot statement for the Carter model. And when it starts to my subset data, let's hold off on that. So if you're using Rstudio, highlight that much down to the plot statement and submit it, okay? And I will do the same thing, except I'll be doing this in R. There we go. Copy. Paste. And off we go. And here are those regression diagnostic things that are actually sort of fun to look at. Sort of interesting, but they're not going to focus, we're not going to focus on it here. Do not include this type of stuff when you submit your papers unless you understand all four of those plots and want to talk about them. But otherwise, these are one of those slides that you'd have in your 50 that you don't use in your PowerPoint presentation and so on. So, but anyway, I do want to show you how it is possible to put these plots in 4 different spots on a nice page where you're talking about these are regression diagnostics, which is sort of interesting to do. But we're not going to use those right now. So let's get to the actual results of the Reagan feelings. Okay. So after you had the Reagan model, and it did it, and you asked for the summary. Notice that after the Reagan model, does everyone see the Reagan model right here? Notice there's nothing printed. There's no output after that Reagan model. Does everyone see that? It goes right to the next line, which is a summary. So if I didn't have that summary, you wouldn't have seen anything. There would be nothing printed. All right? So the summary says, tell me what you did already. I want to see it. So here we go. Well, first of all, it tells a little bit about the residuals. Very minimal, the minimum, the maximum, and the interquartile range, and the median. these are not particularly useful, and we're not going to be focusing on those. If you were doing analysis of the residuals and you really sort of wanted a really basic idea of what's going on with some residuals, you would take a look at those. But that's not what we're going to focus on right now. We want to know about the interpretation of these things. So, first thing, notice that we have the coefficients. It has the intercept term. Even though we didn't ask for it in the model, see, the model didn't say an intercept term, it assumed that there was one that was wanted, and so it gave it to us. There's the intercept term. And the intercept term is 30. So if we're to write this equation out, and there are questions in the final, as well as what you're going to have to do with your big paper, that you're going to have to actually write out the equation. So this one is Reagan feelings in, oops, I'm sorry, this was September. Equals 30.43, I'm using 2 decimal points rounding off, okay? Plus the slope for income. And the slope for income is 0.107, I'm rounding off. Okay, actually why don't I round off the 2 decimal points, make it consistent for everything. So 101 times income plus the age, and the age is 0.1, rounding off, 8, age, plus partisan identification is the variable, and the slope is 4.75 plus an error term. Okay, now this is the actual prediction equation. That means if we wanted to find out someone's predicted feelings, the y hat, the feelings that we would have for Reagan in September, we would say, this is the intercept. What is their income? That person's income. Find it, multiply it times this slope, find their age, multiply it times that slope, add those things together. What is their partisan identification on that 7-point scale? 1 being strong Democrat, weak Democrat, independent leaning Democrat, independent leaning Republican, weak Republican, strong Republican. What is their partisan identification? 1 through 7. What number is it? Multiply it times this number. Add those things all together, and you've got the answer for your feelings for Reagan for that person. There are questions in the final, I guarantee it, where you, and we're going to be asking that in your papers. You're going to be giving how the equations actually make sense. You know, what would a prediction for a particular person be? And so if you have Joe Schmo or Susie Smith, and that's their income, age, and then party identification, you have to be able to say, what is the predicted Reagan feeling? Now, then you might be able to say, what also is their actual Reagan feeling? So, if their predicted Reagan feeling is 83, you know, in the feeling thermometer that goes from 0 to 100, well, it may be that their actual Reagan feelings was 90. Okay? So this would have been your, I'm sorry, this is a y hat, and this is your actual value of y, meaning their actual feelings for Reagan was 90, but they were predicted to have had an 83, which is 7 points below that. So the residual is 7, of course. Actually, it's a -7 because this is below. No, actually, this is, I'm sorry, I got it reversed. This is the predicted and this is the actual. So they're 7 points above the predicted, so the residual would be 7. Okay, when you have y minus y hat, that's the residual. Okay, is everyone all right with that? So this equation is used to actually get the predicted for all the people in your survey. The R square is calculated based on the difference between the predicted, and the actual values. And what you're actually doing when you're getting an R-square using the method of least squares is you're getting the intercept and the slopes that actually give you the smallest possible set of residuals. So if you have, say, in a bivariate regression, an X and a Y, and here's your data cloud, what you're actually doing with the method of least squares, which is what we're doing here. Method of least squares has to do with that R-square thing. You're having the smallest possible sums of squared errors, so you're having your R-squared equals 1 minus the residual sums of squared over the total sums of squared, RSS over TSS. And so remember, this thing is between 0 and 1, so that when the residual sums of squares are the absolute lowest, that's when you'll get the largest R-square and you'll get the least squares line. So that's here. That means they're looking for an equation that gives you the smallest RSS. Now remember, different terminology. Agresti and Finlay used the word SSE, sums of squared errors, instead of RSS. And some people, I believe Michael Lewis Beck, used the letters RSS for regression sums of squares, which is the converse of the residual sums of squares. See, if you have the residual sums of squares, or is the sums of squared errors, that's how much error there is. So if that's how much that the regression equation is missing, what's 1 minus that? Remember, this was also TSS minus RSS divided by TSS. This is the same as this, because TSS and the TSS is 1, right? So what's the total sums of squared minus the sums of squared errors, or the residuals? This will be the amount in the numerator up here that is actually being explained. The RSS, the residual sums of squares, is what's not being explained by the model. It's the error. It's the difference between the lady's actual feelings for Reagan and Susie's predicted. So this was not explained by the model. It's the error. It's the residual. Does everyone get that? Okay? So if this is the residual, what's not explained, what's the total sums of squares around the mean minus the residual? That's how much the model did explain. Does that make sense? Yes? Total sums minus the error will be how much the model actually did explain. So some people like to use the letters RSS to stand for regression sums of squares, and the regression sums of squares is defined as the total sums of squares minus the SSE, or the residual sums of squares. And so they sometimes go like this, and they call that the R squared. And here you're using an RSS, but this RSS has a different meaning. So if you have, it means the regression sums of squares as compared with how I'm using it here for the residual sums of squares. I'm sorry, it's not me who made all of it, but you open different books, you will see different things. I particularly like the use of the word of RSS to stand for residual sums of squares. If you don't like that, use SSE. SSE is probably the one that's used the most. Okay? And some people use RSS to stand for the regression sums of squares, which is simply the TSS minus the SSE, or the RSS over here. So that's how they use the RSS. So if you see the R squared in some book being defined as an RSS over TSS, just remember they're using the RSS to mean something different than the residual. They're using it to mean the converse, which is the total minus the sums of squared errors. Is everyone okay with that? So we've actually shown 3 different ways that you may see this equation. RSS standing for residual sums of squares, or the exact same equation but instead using SSE. Okay? That's probably the most common you'll see. And occasionally you'll see the whole thing here disappear and it'll just be RSS over TSS, in which case the RSS is standing for regression sums of squares. Let me know now if there's anybody who has a question about that. Because you will, every book you open, you'll see one of those 3 varieties. Okay? All right. So let's stick for now, for the rest of the course, with my variety. or my chosen variety of the 3 that you'll see out there. And so what we're trying to do is minimize the error, or minimize the sums of the squared errors. So what we're doing here is we're taking the prediction equation and we're actually modifying it. The actual algebra to do this uses calculus, and so we're not going to do that in this course. You will do that in your next course. It's a very simple derivation for that. But you use calculus to isolate what your slopes will be. You're taking the equation and you're taking the partials of the equation and setting them equal to 0 and optimizing it in the standard characteristic of calculus to get your individual slopes. And you come up with an equation for each individual slope. And what it is basically doing is, the equation is that you're optimizing is one that is for the least squares of the errors, the sums of squared errors. And so what you're actually getting is a value for your slopes that minimizes that sums of squared errors. That means you don't want a line that goes like that because the error will be larger. You don't want a line that goes like that, the error would be huge. You don't want a line that goes like that, the error would be, you want a line that will minimize this guy. And they use calculus to derive that. This brings us to one other point. Why are these linear models of the type you see here, where you have a slope for each variable and an intercept all added together, why are those so common in graduate work and in professional life using statistics? It is because in your next course in statistics, you're going to actually go through the derivation of the equation for these slopes and the intercepts. And those slopes and intercepts were derived by statisticians. Very simple derivation for that. And they work with an equation that is a result for each slope. And it's easily programmable into a computer program like R or Stata or SPSS or SAS. And that equation that says this slope equals is just something they code out and it's done. So with statistics, you're already seeing a problem in statistics. You're using a model that was actually written by somebody else. You're using a model that has empty spots in it. Here it is. This is the empty spot. This is the empty spot. That is the empty spot. Those are where the independent variables go. What you're doing is picking different independent variables to go in these spots. That's what graduate students spend 99% of their time doing when they're getting to do dissertation research. They're looking at a data set that has a whole bunch of independent variables and they're trying to pick which ones go there. It's sort of stupid, but that's what actually goes on. It's actually very useful because with multiple regression you actually get an idea of what variables are influencing the dependent variable. But the reality is, this linear model probably is not a very good representation of what happens in the world. Go outside after this class. Look anywhere. Find anything that's made by nature that's straight. It just doesn't happen. Only humans make straight things. We made straight lines for each one of these variables. Look at leaves, look at trees, look at rivers, look at mountains. Where do you see anything that's straight? Well, human behavior is not going to be any different. So the reality is, existence is nonlinear. So this model is probably not a good model. But listen to these words. It's good enough for government work. Meaning, it's good enough to get the basic idea of how this variable, this dependent variable, is actually working. So that's what we do in this level of statistics. If any of you ever take my advanced course, 490, is modeling complex systems, the only thing we deal with in that course is nonlinear models. That's what I'm famous for. That's what I'm well known for. I do nonlinear modeling, differential and difference equation modeling, overtime stuff, but nonlinear stuff. That's my passion. That's what I actually do. But I always start out with these statistical models. And I have published straightforward linear statistical models as well. So I'm not saying they're useless. They're actually very useful. 99% of all statistics uses these linear models. They're very valuable. It's just, you have to understand, even when you're getting into it, that they're really not the end of the story. Why do so many people in graduate school do their dissertations based on the linear model? It's because they've taken courses up to the linear model and they essentially want to stop and just use it, get their dissertation, and move on. It takes that added layer of training to be able to do the nonlinear stuff. It's like being a doctor and becoming a specialist. Now, you go to medical school, 4 years, and you go to your residency, internship, so on like that, and you finally become a doctor. What if you want to become a specialist? You got to go back and study under somebody else for another couple years. Do you get the idea? You have to do specialty stuff. And then you want to become a specialist. You have to go back and work under somebody else. You're sometimes in school, medical school, or working in hospitals under other people, getting that extra training for an extra 10 years. And you see people who sometimes finish their training like in their 40s. If they're specialty. So with social sciences, it's not that bad. But the point is, when people have a 4 or 5 year span for graduate school, they really want to get into that dissertation, get it done, get a job, and get out. And so they often stop at the linear models. And that's why so many people do the linear models. To do the nonlinear stuff, you have to go above and beyond. The passion has to be there. You have to want to be able to do it. And you also have to know things like calculus, differential equations, overtime stuff. You have to be introduced to that. It's a whole nother level of mathematics where you actually use stuff you're learning in the math department, not just stat stuff that you're learning in social science programs. So it's a whole nother type of thing. I'm a mathematician. I'm a member of the American Mathematical Society. I go to the meetings, that type of thing. I talk with the math people. Do you get the idea? So this is sort of what I like to do. The reason I'm mentioning this now is I want you to understand the statistics. It's what you have to know. But I also want you to know at the beginning what the limitations are. Okay, secondly, what about this stuff, these independent variables? They're called exogenous variables, independent variables. All right? So what is that stuff all about, actually? Well, let's use the word independent rather than exogenous, so I get the same idea with it. What they're basically saying with statistics is that the dependent variable is over there. Reagan fields or Carter fields. Okay? Here's the dependent variable over here. And these are exogenous, these independent variables. They're independent of anything else. They're standing under the sun like a tree in the field all by itself and nothing's messing with them. Okay? And these guys, and I mean guys always generically, men and women, these guys are affecting that dependent variable. So this dependent variable is like a puppet on a string being affected by those guys. And these guys are independent of everything. They just stand here under the sun. You get the idea? That's the nature of the word exogenous or independent variables. And that means that that dependent variable is the only one that's depending on these ones, and these ones are not depending on anything. That's really stupid. Agreed? I mean, just think about it. The reality is, everything affects everything. This is a yeasty, like bread, all mixed together, frothy, nonlinear, tumultuous world. But statistics is based on the idea that these things are independent, exogenous, out of the system, and they're affecting that thing, and that thing's a puppet on a string being affected by it. So that's the conceptualization of statistics. It's actually very useful to get going. And for even doing dissertation work, it's actually okay to keep thinking about that. But just understand in your own mind, something that you probably will not be exposed to in your next course in statistics, is sort of my flavor of things, is that that is really an artificial divide. In reality, stuff that happens over there affects stuff that happens over here. There's all types of relationships going back and forth. They're sometimes very difficult to find out. There's all types of feedback stuff that actually happens. But for the basic approach to statistics, it's a one-way street. This stuff here goes that way and affects that dependent variable, end of the story, and you're trying to show how that influence works. Okay? So, this is good in a sense. You get a tremendous amount of stuff on it, but it also has its limitations. Some of you actually might be inspired in something. Now I know a number of you are either joint majors in math and political science or straight majors in math or math and economics. So some of you are very talented with math, and you may actually go into some of this stuff later and start looking at some of the nonlinear models and the feedback stuff. You know, you're very capable. Remember, Remember what I said with that one lecture? You're the best of the best. You sometimes don't know it because you've always been among the best of the best. Your peers have always been the best of the best, so you don't know how good you really are. But just remember that, okay? That at some point, some of you are really talented and may actually want to go to the next level beyond the linear model. All right, so this right here, we're having these slopes, that intercept, that's the model, and that's how we got the predicted value for y. Okay, now let's look at what else we get. We also get the r square. Here's our r square, 0.1487. Nah, it's not too good. I've seen worse, but it's all right. All right, I'd like to have it a little higher. That's not very good. What's the difference between this multiple r squared and the adjusted r square? Well, the r squared that's this simply multiple r squared is what we've been talking about all along. The adjusted r squared is different. You see, you can take any variable you want, just random noise, just random numbers, make a variable out of it, and throw it in the equation as another independent variable, and your r squared will go up. The least squares model will find something in that stuff that will improve the fit a little bit. Just by chance, it'll find something. So your r squared will go up. So just by adding new variables, you're increasing your r squared. Hey, that's cheating. I mean, anybody would know that's cheating. You could throw a whole bunch of junk in there and until your r squared eventually gets really high. So what the adjusted r squared is, the adjusted r squared takes into consideration how many variables you have. So if you throw in a lot of junk that doesn't do anything, your r squared is not going to go up with the adjusted r squared. Is it okay? Also, if you have two different models, one where you're doing Reagan feelings with 6 variables, independent variables, and another where you're doing Reagan feelings with, say, 10 independent variables, if you just look at the r squared for the 10 will be higher than the r squared for the 6. But what if those extra 4 variables really didn't do anything? Your adjusted r squared will indicate no improvement whatsoever. So, if you're comparing models that have different numbers of independent variables, you always look at the adjusted r squared. If you're comparing models that have the exact same numbers of independent variables, it doesn't matter which one you look at, so you might as well look at the regular r squared. Okay? Is that all right? Different numbers of independent variables for different models, look at the adjusted r squared. So what is this F statistic? This is a really interesting statistic from a statistical point of view from the perspective of statisticians. So if you take a course from some of my friends in the math department in stats, they'll talk about how interesting that F statistic actually is. It tests the significance of the entire equation. Now let me tell you the truth. That is one of the most useless statistics ever invented by man. Not the F statistic. The F statistic is actually a modification of a t-statistic. If you take a t-statistic, one of these guys, and square it, you actually have an F statistic. There's nothing wrong with an F statistic. That's not the problem. The application of the F statistic right here is just not useful at all. So if you get a course from a statistician, they'll wax and wane about how wonderful this F statistic is because it tells you the significance of whether this entire model tests for feelings for Reagan. Why is it so stupid? It's almost impossible to get a p-value that's not significant. You just throw a whole bunch of regular old independent variables in there that are hardly worth anything and you'll still get a p-value that's significant. I've never seen it reported in the scientific literature. It probably has been, maybe I just didn't notice it, but they don't even include it in tables. But it does test whether the general model is significant in predicting Reagan feelings. But it always is significant, predicting the dependent variable. It always happens. You can probably come up with an equation where it's not significant, but you probably have to try pretty hard to get one. Okay, so this statistic, as interesting as it is from a theoretical perspective, it's not very useful from a practical perspective. So do not include this in your actual output when you actually write up your tables, okay? That little F statistic. We will actually cover the F statistic later on in the course. Anyway, so this is very nice. Now the trouble is, when we look at these numbers, and the ones for Carter are the same, it has the same parallel structure. So if I was looking at Reagan feelings and comparing them with Carter feelings, I have them right here. The exact same model, parallel structure, and the same number of variables. The R squared is a little better for the Carter feelings. That means these variables, these exact same variables, do better in predicting Carter feelings than they do Reagan a bit. Not that much, but a bit better. And these are the slopes, and so on. So let's just focus on the Reagan feelings for a second. Let's go back a little bit. The problem here is that now I have an ability, which is important, to predict my feelings for Reagan based on those three variables in my intercept. But what I'd really like to do is to be able to know what was the most important influence in creating the feelings for Reagan. Was it partisanship or was it the age? Maybe it was just a bunch of old people who were voting for Reagan. Maybe it was age that was really the big determinant. As people got older, they voted for someone who was older. Maybe it was income. The rich people were voting Republican. So as people got richer, they were voting Republican. Maybe that's what was going on. Which of these variables is the most important? Is income more important than age? What about, is income more important than party ID, or is party ID more important? Now remember, party ID goes from Democratic to Republican. So as you get a higher value in party ID, you get a higher value in Republicanism. And look at the slope. The slope is positive. So your value is, your feelings for Reagan are going to be higher as party ID gets higher. But like, which one is the most useful? Well, income is an income scale. Age is years old. Party ID is that 7-point scale. This isn't very... I can't compare these slopes. This is a party ID that goes from 1 to 7, but it has apparently a big influence on Reagan feelings, because here you have age going from 18 up to 100 or something like that. But because these are different scales here, this slope times that scale is going to be different from this slope times that scale. So what do I do? Oh, one other thing. Notice when I wrote this stuff out, I wrote out income, age, party identification. In none of your papers should I ever see any indication of an actual variable as it's spelled in the computer code. Spell it out. No computer code in your actual papers. For your variables, I know it's more letters. Partisan identification. Don't put party ID. Income. Don't use inc. Use income. I-N-C-O-M-E. Spell it out. No computer stuff. Okay? So, what we have here is a desire to be able to compare these slopes, and we can't because the scales for the slopes are different. So we want to use standardized regression coefficients where the scales are exactly the same, standard deviation units. So we're going to do that in just a second. Now let's go over here. Let's look at the standard error. These are the standard errors for all of your slopes and for your intercept. And now we're always testing against the null hypothesis, which is the slope equal to 0? If the slope is 0, it's a flat line. That means no matter how far you go up in income or party ID or age, you're not going to go up in Reagan feelings. You got a flat line. So we're testing that null hypothesis. Your alternate hypothesis is, no, that variable really matters. So you want it to be different from 0. So how do we do that? We test the difference between that slope and 0. So that slope minus 0, which is just that slope, divided by the standard error, will tell you how many standard error units in between that number and 0. And if you have 1.96 or better, 95% level, it's different. Real simple. So that's what that t-value is. You simply take your standard error and divide it into your slope, and that's your t-statistic. Now you could then look that up in the back of the book, but like everyone knows you're going to want it. So R just pumps out the p-value. So you don't have to look it up in the back of the book anymore. The p-value is right here. And you see that scientific notation? So that means that's a really small p-value. Income indicates that that variable wasn't very useful in predicting. The p-value there was 0.51. That's a terrible p-value. The p-value for age actually was okay, 0.001. That beat the 95% level. It beat 0.05. The p-value that you're looking, the alpha level of the test is 0.05 for a 95% test. So this 0.001 is less than 0.05, so that beats it. This is way less than 0.05, so that beats it. This one is not bigger. This 0.51 is not bigger than, or actually, I meant more significant than, that's how I meant bigger. So I meant actually smaller. So this one is not smaller, 0.51 than say 0.05. So this one's not so significant, that one is, that one is. Now, some methodologists will, sometimes you'll be looking at something like this and say, so income's not so important, age and party ID is. And you will get occasionally some methodologists who will say, that's wrong, that's stupid. And they'll criticize you on that. And you say, what are you talking about? Look at those p-values. And they'll actually come back to you and say, these are a couple of my favorite arguments that I see methodologists making. I love when they make them because I like to get into arguments with them about that. They say, the p-value is useless. It's not very important. You can always increase the p-value by having more people in your survey. Just have more people in your survey and your p-value will go up, will get smaller, and you'll get significance. So what we really want to know is the slope. Is it positive, negative? Tell us an interesting story. And it is true if you have more people in the survey. But that's, from me, such a stupid argument because you don't have more people in the survey. The money ran out. That's it. You can't go back and reinvent the wheel. Those are all we have. So based on the amount of information we have, the significance of income in that equation is not good. And so it doesn't influence Reagan feelings. So the methodologists are correct sometimes when they say, oh, but that's not correct because p-value depends on the sample size. You could always increase the sample size. But the argument against that is it wasn't done. We don't have a bigger sample size. So based on what we do have, we cannot judge, we cannot reject the null hypothesis. Do you understand? There's that argument. You just have to be ready for it. So when they say, oh, your results aren't so, this is not so, because in the old days, what people used to do is they just used to leave, they sometimes used to leave the sort of an asterisk inside the values that are not significant and not even give the value. And they would just say, that's not significant, so don't look at it. And the methodologist correctly said, no, I want to see it. But then they, in my view, incorrectly said, because what it really does is it really matters, because we could always increase it, we could always change the significance by just increasing the sample size. The reality is, if they did increase the sample size, this significance indicates that there's no guarantee that this slope wouldn't change in sign or go in some other, get larger or smaller. There's no guarantee of what this thing would actually do. So the old days of actually just leaving it blank were wrong. You do have to put all of the numbers in the table. So that criticism is correct. But you can't really put much weight into this number if it's not significant. That's the point that I'm trying to make. Print it, include it, but note that you really can't put much weight into the discussion of it. And it is true you could increase the sample size, but you don't have the money, it wasn't done, this was done in 1980, you don't have a time machine, it can't be done. So based on what we have, this is the best we can say. All right, let me see, oh, and they print out here the significant codes, but you already know those. That's what the asterisk stands for. Like, this is really significant, but you don't really need this stuff here. The asterisk, you can just sort of ignore these p-values. All right, now there's one thing I want to show you of what this stuff looks like if you don't use scientific notation, and then we will go into the standardized regression coefficients. So I'm going to go back here. And for myself, I'm just going to pick out, let me see, do I have I had this machine reformatted, so I could pick out a bunch of stuff. Let me just go to the accessories and get WordPad. That'll be quick. So I'm just going to paste that stuff into WordPad. And now I'm going to go to the top here. And you see here, where I have the options, SciPen equals 20. Well, I'm going to get rid of this pound sign, and I'm going to put a pound sign in front of this one where the SciPen equals null. Brings things back to normal. So I'm going to activate this one, get rid of the pound sign, making it, it's currently a comment. I'm going to get rid of the pound sign and make it work. And I'm going to put a pound sign in front of this one and make that one not work. And then we're going to run just the eigenfeelings again so you can see what it looks like. So let's get rid of the pound sign. And then let's put the pound sign back. Let's put the pound sign in this one. And then what I'm going to do is I'm just going to go from the options to the eigenfeelings. That's all I'm going to copy. I'm just going to copy the option statement and the Reagan model and the summary. And that's all I'm going to put into R again. Okay? So let's do that. Okay. Let's take a look at what the results look like. You see what it looks like without scientific notation? You see all these zeros? It spells out. It doesn't give you the scientific notation. It actually puts all the zeros in front of those decimals. And so if at some point you actually want to see what those numbers look like, there it is. Here's your p-value for the entire F statistic. That's what it does. I personally don't like this. I like the default value, which is with the scientific notation. But without the scientific notation, that's what it looks like. Sometimes that is sort of fun to play with and a little bit useful. All right, so let's go back here. Oops. And what I'm going to do is reverse what I just did. Okay, and I'm just going to copy that option statement. And you can run this option statement. This is the one that turns the scientific notation back on. I'm going to run that thing only in R, just so I get my scientific notation back on. Okay? Now let's go to here. This is where I start with my subset data and go down. Everyone see? From here, my subset data down. Here I'm going to get my standardized regression coefficients. Okay? So the first thing I want to do is make a new data set, which is why I don't want to have the attach command floating around. So I have a new data set, my subset data, and here I didn't put a little space before the less than sign and a space after the dash. Why? Because this line was getting pretty long and I wanted to try to squeak as much as I could in. But it's generally better to put a space before the less than sign and after the dash, just to make it more readable. And also sometimes you have equations over here on the right hand side that have negatives in them, so you don't want them to go right next to them, or sometimes mistakes can happen in terms of you coding it and getting it all right. You may mistake your negative sign for that part of the assigned sign and so on. So a little space helps clear things up. So I'm going to subset my data. This is the same type of thing we've done. And I'm going to select the variables, Reagan-feeling, Carter-feelings, actually Ray-field 3, Carter-field 3, income, age, and party ID. And that keeps only the variables that we're using. I'm going to standardize those variables, so there's no reason for me to standardize the whole data set. Okay? I mean, I could have standardized the whole data set, but this just makes it nice and manageable because I'm going to print out some tables and I want just those variables in the table so they fit in the space on the screen. All right. So the first thing I'm going to do is get the correlations. Now this is the correlation matrix for the variables in the regression. So this is a variable, this is the very thing. This is the small r. Everyone remember my discussion of small r? Okay, so that uses the small r goes from -1 to +1. So let's actually just do that. So if you're using Rstudio, do that now. Just get the my subset data line and the correlation, the core procedure, which is the correlation coefficients. And just highlight that and run it. And here we go. Actually, hold on here. There it is. Looks like I highlighted more than. What did I do? Hold on, let me try that again, okay? Copy. paste. Okay, that's better, I think. So, yeah, there we have my options statement, and we have just the correlation coefficient. Actually, I did it twice, the exact same thing. So this is the one I just printed the most recently, but this is the exact same thing. All right, now these matrices they reflect on each other. So notice that the correlation between eigenfeelings and Reagan-feelings, meaning the matrices, the row values are the same as the row variables are the same as the column variables. So you have ray field 3, car field 3, income, age, party ID, and going across the columns, the same thing. Ray field 3, car field 3, income, age, party ID. Now, what is the correlation between Reagan-feelings and Reagan-feelings? It's going to be perfect, right? And there's no difference. They're the same exact variable. So it's going to be a perfect correlation. What's a perfect correlation? The number 1. Okay? That's the same as with a plot. That's the same as here. Reagan-feelings and Reagan-feelings. The exact same variable on both axes. A 45-degree line. The slope of 1. With the same exact, and of course these are standardized variables, but in this case it doesn't even matter, but that's what the correlations actually are. So look here, look at the diagonal values of this correlation matrix. 1, 1, 1, 1, 1. That's because every time there's a 1, you have the exact same variable on the row as you have on the column. Now, all the other variables are mirrors. So this is negative 0.1965 for the correlation between Carter feelings and Reagan feelings. Okay? Notice here the correlation between Reagan feelings and Carter feelings. The variables are switched, but they're the same two variables. It's the same number. So everything on the lower part of the diagonal will be the exact same number as everything on the upper part of the diagonal. It's a mirror. So with the correlation matrix, you only have to look at above the diagonal, or if you like, below the diagonal. But you don't have to look at both. Are we okay with that? This tells us that there's a negative correlation between Reagan feelings and Carter feelings. That means as you get higher in Reagan feelings, you have lower feelings towards Carter. And that makes sense. You see that negative 0.19? That's what that's about. And similarly, there's a negative correlation between Carter feelings and party ID. As you get increased feelings in Carter feelings, party ID goes from a low value for liking the Republicans, a low value for liking the Democrats, to a high value for liking the Republicans. So as you go with increased values for Carter feelings, you have lower values, meaning liking the Democrats, for party ID. Actually, those are not feelings for the party. Party ID is whether the respondent identifies herself or himself as, a Republican or Democrat. So, Reagan positive Carter feelings has a negative correlation with party ID. That means as you get higher feelings for Carter, you're dealing with more Democrats, not Republicans, because the higher values for party ID will be Republicans, the lower values will be Democrats. Are we okay with that? So that's the correlation. Now, this correlation coefficient, these are the Pearson product moment correlation coefficients, or just correlation coefficients. Now let's actually get the covariance matrix for the coefficients. Gosh, let me click that. Okay, good. I'm getting the next line, which is the covariance matrix. Okay? Now the covariance, COV, is actually identical to the VAR. I don't know why they never sorted that out, but somebody out there in the internet world, in the R world, liked VAR better. and somebody liked COV better. I sort of like COV better. But they do the exact same thing. The only reason I use covariance here and VAR there is just to show you that they do the same thing, so that you get used to the idea. If you ever see a VAR, you know you're dealing with COV. What is the variance and covariance? Let's actually think of this way. When we were dealing with the variance of a variable, we were dealing with, let's use y, okay? Well, actually, let's use an x because we're dealing with independent variables. So this x minus its mean squared, added it up, okay, divided by n minus 1. Okay, let's not worry about what you're dividing by right now, all right? Let's just look at the top, okay? Let's just look at the top, x minus x bar. Variance around the mean squared. Covariance is where you're looking at, as one variable gets higher around its mean, what's happening with another variable around its mean. So what we're dealing with, the concept of covariance, is summing up not the same deviation squared, but you're getting two variables. So I'm going to go x1 minus x bar 1. That means x1 minus its mean times x2 minus its mean. That's what we're talking about with covariance. So it's the difference, the variation, the difference between x and its mean for the first variable and x and its mean for the second variable. So as one gets bigger, does the other one get bigger? Or as one gets bigger, does the other one not do anything? Or as one gets bigger, does the other one get smaller around its mean? Does it make sense? But that's the idea behind covariance versus variance. That's why I like the letter COV rather than VAR, because COV has that concept of covariance. So this is the covariance matrix for the coefficients. So let's actually print that out. I got 2 minutes. I'm rushing a little bit, but I think you're following. If you're not, I'm really depending on you to say, Courtney, stop. Okay, so but I'm hoping this is going to work. And this is where the video of the classes is actually useful. You get to rehear it all over again. I'm covering some things that are not all in the book also. Okay, so now let's look. We have the covariance. So there it is. There we go. Here it is. I was wondering where it went. Here's the covariance. So this is the variables that are the covariance between the variables. Okay? Now the correlation matrix is actually based on this covariance matrix. Just by itself, this covariance matrix isn't so useful. But it is used in the construction of all of your statistics coming out of linear regression. So you're actually going to use this covariance matrix in your next course in statistics a lot in terms of diagnostic stuff. We're actually going to use that a little bit when we cover ridge regression. It's actually a very useful thing. But right now I just wanted to show you the concept. This is standardized variables versus unstandardized variables. This is covariation with standardized variables, covariation without standardizing them, so you have the original units. Now let's look at what happens. This is the, as Johnny Bravo would say, this is the coup de grace moment. Now let's standardize the variables. And we're over. So let me just summarize what we're going to do as soon as you walk in on Tuesday. All right? And what you're supposed to be doing over the weekend is coming up with a set of no fewer than 5. 5's not good. I don't like 5. No more than 10, just to start. Independent variables that have a nice prediction value, nice R-square, significant t-values, and so on like that, for your Carter feelings and Reagan feelings. So I'm going to come in here and say, what have you got? And I want people to say, the regression didn't work, what did I do wrong? Or hey, I got it up to 0.8, or I got it up to 0.5 or something, or I got it up to 0.25 or something. What we're going to do now, when we start on Tuesday, right after I find out if you got results, because that's what the homework assignment is going to be about. You're going to have to start writing it up after Tuesday. What I'm going to do now is, when you come back, go through these lines, which will get our standardized regression coefficients. And what that's going to do is going to take the actual variables, standardize all of them, and then with the standardized variables, everyone get that? With the standardized variables, I'm going to do the correlation matrix. I'm sorry, I'm going to do the covariance matrix again. That covariance matrix that had all those big numbers in them, I'm going to redo that with standardized variables. And what you're going to get when I do that using the VAR instead of the COV, just for the heck of it, I could have used COV, you're going to get back your correlation matrix. You're going to see, so that's what that correlation matrix was. It's just a covariance matrix when everything is standardized. And that will connect up with the last lecture where I actually derived that thing for you. Is that okay? How many variables are you going to have on your independent side for both Reagan and Carter feelings? No less than 5, right? And you can stop when you get to 10. All right? See you on Tuesday. Have a good weekend.
Mm-hmm.